Hello everyone, I'm just doing a quick audio check. So if you're in the chat waiting for the train to arrive, which is strangely on time today, which almost never happens. Hi Alka, I see you waving there. Let me know if you can hear me okay. I know the balance might be a little bit off with the music playing underneath me, but the music won't be playing during the stream. So more just a quick check to know that you can hear me, and we'll be getting started in just a couple minutes. Let me know where you're watching from. I always love to know where people are around the world watching. All right, I have to say hi to what I think is one of my students who graduated last year in the chat. Nice to see you there, lovely. The song is a bit longer than my countdown. I realize it's at 0. Here, I'm gonna bring myself on screen. Hi everybody, it's lovely to see you. Oh, wow, here it is. I don't have my train whistle. This is the one that requires a really exceptional amount of air to make a sound. It's the older train whistle. I've got to find my newer one, which has a more of a robust carving inside to really unleash the true sound of the train whistle. Of course, I also have my authentic 1950s Danish train whistle somewhere in a very safe space around here, thanks to Stig, who I saw many years ago now at Processing Community Day in Copenhagen, and who was part of a group who gifted me that train whistle. So, you know, I collect train. Hi, welcome to YouTube, the Coding Train. I'm just talking about train whistles. My name is Dan. Maybe you're new here. Maybe you watched me for 10 years. Maybe you just watched a couple videos before. Maybe who knows? But you're here, and I'm so thankful and glad that you're here for a special pre-school year August live stream. And you might be somewhat surprised to see me in the sense that I have actually now this is my 3rd live stream this August. And prior to this August in the last year, maybe I did 1 live stream too. As I've talked about in the previous 2 streams, I'm really trying to get back into the groove. Maybe towards the end, I will talk about and remind you what's coming next from the Coding Train. I will be streaming regularly. Every Monday, I have a list of topics and ideas and things that I'm going to be teaching and experimenting with and trying All of that is coming in the fall. But today I'm really excited to have another guest here on the coding train. This is another thing that I have been attempting to organize myself around better. Last time, if you missed it, go back. Don't go now, because I want you to stay here. Of course, if you have something else to do today, that's also okay. Maybe you want to go outside, get some sun, be with family and friends. You don't have to stay glued to your computer. However, if you're going to be on your computer, you might as well watch this, because I think it's going to be fantastic and awesome. And of course, if you're not able to stay, the archive of this stream will be on YouTube, for however long YouTube exists and that I choose to stay on that platform, which, for the foreseeable future, I think that we can be fairly confident that that will be the case. But the previous stream, Kit Kuksinak from the Processing Foundation, the lead of the P5JS JavaScript library, which is the primary coding library and online editor and sort of community that I teach with, that I work with in all of my videos. So if you wanted to learn a bit about what's coming in P5 2.0 and how you can start to experiment with the beta of P5 2.0, all of that happened in the previous stream. But I want to talk about what's happening today. So, and I'm just sort of checking the chat. Nobody is saying I can't hear you, there's static or anything like that. So that's good. All right, I'm going to pull up my laptop here, and what you are seeing is the archive of a stream that I did on July 16th, 2022. Now, this is not so unusual for the coding train. Notice the title of this stream. Oops, there's a little error message that's popping up that I just have to click a button here. Apologies for that. It's nothing to be alarmed about. These error messages they're very common. I can get past it. Okay, but looking at this stream, what I want to highlight here, right over here, is this part 1. Now, if you see something titled part 1, typically what that means is there will be a part 2, maybe even a 3. Who knows? It could be in 5 parts. I've watched things that have 10 parts. Who knows how many parts you can have? July 16th, 2022. Well, today is the day I am here to deliver on the promise of part 2. And so I know it's over 3 years later. I do really hope there will be a part 3 and that you won't be waiting 3 years. So that would be kind of interesting to just every 3 years we do another part. But anyway, so let me just take a look. So first of all, Dr. Christian Hubicki is waiting in the wings. He's here to join me again for this part 2. Wouldn't make any sense to do part 2 without him. So I'll introduce him in a second. But and actually, let me do that now, and then we'll come back to this and talk a little bit about what we did, because I've already gone on for too long. So maybe you watched part 2, maybe you already follow Dr. Hubicki on the internet, but if you don't know, haven't encountered his work, Christian Hubicki is an associate professor of mechanical engineering at the FAMU FSU College of Engineering. He runs a research group called the Optimal Robotics Laboratory. They specialize in legged robots. Is that the way you say that? Legged? Leg?
Yeah, that's it. Yeah. Perfect. Or you could also be legged, we're not picky.
Okay. Applied optimal control, biomechanical modeling, and fast algorithms for adaptive robotics behavior. He has a bachelor and master's degrees in mechanical engineering from Bucknell University and a dual degree PhD in robotics and mechanical engineering at Oregon State University. I think Dr. Hubicki might be the most qualified person I've ever had, certainly to talk about robotics here on the coding train. So let me bring him here into this guest view to say hello. How are you doing, Christian? So lovely to see you too.
I'm doing great. I'm excited. Yeah. I'm sorry. I apologize. I'm already that delay. Did you know there's a science to the delay that there's a speed of light issue for one, but that's probably not what we're dealing with. But the Ig Nobel, the Ig Nobel prizes. You ever heard of the Nobel? There's the Nobel Prize and there's the Ig Nobel Prize for silly research. There was an Ig Nobel Prize that went to someone who created what they called the shut up gun, which is what they do is they put a gun that measures that has a microphone, and it plays back to you whatever you just said with just a tiny delay, and it forces you to stop talking. And I feel like that's what I just did to myself right now. I'm sorry. But anyway, it's good to see you.
That's incredible. I don't think that I try to think of what are some achievements I could aspire to in my life, and I've never considered the Nobel Prize. I think that's way out of reach. But the Ig Nobel Prize, I think this is something that I could maybe, think about. And silly research sounds like something I might actually be able to achieve on a level of excellence that could possibly qualify me. Do you have to self-nominate, or how does that work?
I think I'm not sure if you can you probably can self-nominate. I know there are people who gun for it. I'll be honest. There are people I know who are like, I want one. So it might be some stiff competition, but I believe in you, Dan.
Yeah. Okay. Well, we'll come back to that another time. We can have a sidebar later and talk about if there's some collaboration we could do that might set us up for success with the Ig Nobel Prize. Well, I'm so thrilled that you're here. I mean, one of the things to me that is, I think, well, there's so many reasons that I love having you here on the channel. Number one is I really live in this software world. And I think a lot of the viewers who watch and learn about code and learn about simulation and how to, create even art with code, they're people who are building, working with microcontrollers or working with hardware, LEDs, and maybe even, servo motors, dare I say robotics. They're people who live in the physical world developing hardware with technology. And so I like to be able to excite and those people and bring learning to them in a way that's exciting and engaging. So I think having a little window into how some of the work that I do in simple JavaScript simulation programs could actually apply to real world physical mechanics of robotics is really exciting, I think interesting for me and hopefully for the viewers.
No, for sure. I mean, and I love watching your videos. I'm stunned by this sheer quantity and scope of what you cover on them, and it is quite relevant. You're right on the money in that more than ever, it's important to have decent simulations of your robots to get them working. In fact, I mean, we'll get into the subject matter of today, which is about how to get robots to hop, because I think this is something that we can do within the scope of a single stream, or at least get the good flavor of it, right? But like for a long time, simulations were slow, but just good enough that if you wanted to write a simulation of your robot and try a controller on it, so I do robot control. I guess we'll get into this presentation in just a minute. That they were just good enough to help you develop a controller and be like, it'll probably work. Then you try it on the robot, and it might work, it might not work. But now they're getting much better. And to the point where some people will, go on, please,
No, you finished. I did the interrupting thing again.
Oh no, it's what we will do. We will do this to each other constantly throughout the stream, I'm sure. But like now it's to the point where people have massaged the controllers and simulations enough that they will just have a computer optimize the controller and simulation and just put it on the robot, and it'll probably work. That's actually a huge accomplishment. Probably in the last, I would say, 6-7 years that's certainly less than 10 years that's been the case. So it's a very exciting time in the world of robotics. So maybe I should give people more context as to what the heck I'm talking about. But I'm just so excited. I'm just jumping right in.
Yeah. So let me just say, I'm going to say a couple things, and I'm going to let you get into your presentation. So one is, let me just bring up here what we did previously. So to me, the other thing I think that is the point of connection here is when you're doing simulations in the lab, often the environment that you're working in, maybe I know we've had some back and forth where you'll send me some example code, and I think last time we did some stuff in Python, you sent me some MATLAB code, where often the code itself and the result of it is very technical and doesn't not necessarily like real time or interactive. So that's one of the things that we, just to refresh people's memory, that we did last time. We have this, I think of this as the cart pole. Is that the right term for this simulation?
It's one of many correct terms for it, Dan. That's perfect.
Okay. Upside down pendulum. But if people remember from last time, this is a controller that, as I apply a force to this inverted pendulum, I guess is a way to say that, the controller is optimizing the movement of the robot to be able to balance the pole. So the thing that I wanted to mention about this is, for me, what's really exciting that I want to try is learn something from Christian, this is what we did last time, about the theory and math behind how this works and see if we can make a real-time system that you can actually interact and play with work. The other thing that I want to emphasize just from the outset, and maybe we'll come back to this a bit more later, is I think often when you see something like this, you think, what fancy AI system did you make do this? And I think it's very easy, especially in any sort of technical field or even in a sort of creative arts field with working with technology, to think like, oh, I need the most powerful, biggest, especially now with all of the sort of hype and everything that's happening, I don't want to get too sidetracked here, GPU and the fanciest, biggest algorithm to solve this problem, where actually a very classic algorithm that just is a few lines of code with a little bit of math that could run on like the tiniest computer is great. And I assume that that's also highly relevant because a robot that's going to be untethered out in the world it can't necessarily be like, let me send all my data to the giant cloud computer to like wait to get the answer back of how I need to move my hopping leg. So those are two things that I just wanted to emphasize about the sort of context, I think, of what we're doing here.
Yeah, and I'll add on to that, as a person who kind of grew up academically and learning these more classical methods, obviously I have a bias toward them, but I mean, clearly there's these wonderful, AI-driven methods or reinforcement learning or deep learning methods that people use. But when you see, and I'll get to this in the presentation, but even the most sophisticated and advanced, amazing things using deep learning to make a robot go that you might see on YouTube, down at their core, are using the controller that Dan just showed. And we'll do a review of it. It's called the PID controller. That we'll need to do a quick review of that from the last stream. That's okay. We'll get straight through it. And we'll use that and apply it in an interesting way to make a robot hop. So anyway, it's important to know that even if you're interested, and you should be, in these coolest, newest deep learning frameworks, they at their core do use these classical methods because they just work at a certain level.
Yeah, wonderful. Okay, so we're gonna get started. We're gonna move on from our chatting phase of the live stream to get started. Let me just give you a kind of outline of what's gonna happen. I'm gonna turn the stream over to Christian to talk a bit more about himself and his work and explain the PID controller, the hopping, what a Raibert controller is, all that kind of good stuff. While he's presenting, I'll be keeping an eye on the chat, so put your questions in there, and I'll kind of like keep track of some of them to ask. Towards the end of the presentation. Once that finishes, I'm going to pull up some P5 code. I'm going to listen very, very intently, because my job, with Christian's help, will be to start to implement the concepts in a simple P5.js sketch, and we'll see how far we go. Our goal is to wrap this up in under 2 hours. So we'll be here for probably another hour to hour and a half. So you can remind me as it's getting late that I should, everybody needs to eat lunch and move on with their day. And whatever we don't get to today, we can follow up with on social media, in the Coding Train Discord, and even in a future stream. Okay, so I'm gonna switch over the screen to put you full screen, Christian, and take it away.
No, fantastic. No, so today the subject is going to be how to make a robot hop. All right, and that's what we're going to try to cover today, and how this fits into the greater history of how robots now walk. I'm sure many of you have seen, or like, there's so much news actually about humanoid robots, especially in the past 3 years. There are dozens and dozens, probably well over 100 humanoid startup companies that are trying to make robots that walk and do real life things. But let's get into it, okay? So first off, who am I? I'm Christian Hubicki. I'm a robotics professor. I have a PhD in robotics and mechanical engineering, and I run a robotics lab where we focus on controlling legged robots. We do other kinds of robots too, but that is my bread and butter. That's where I grew up. That's what I cut my teeth doing. And so a little history is sort of where I come from here. So I did my undergrad at Bucknell University in central Pennsylvania, and I did some simulation of legged robots there. I then went to Oregon State University for my PhD, where I controlled some bipedal robots. I was part of a team that made this human-sized robot that would walk around. And I did my postdoc at Georgia Tech, where I did some postdocs in physics and mechanical engineering, where I did more robot control. I'll show a little bit of the robots I controlled there. I took a brief stay over in Fiji for the television show Survivor. I'm covering up my own face when I was on Survivor right there. Perfect, just so you can't see me. That was a fun little distraction, but a fun time. And And now, it was right after I filmed that show and it aired, I became a professor at the FAMU FSU College of Engineering. So I'm a professor at Florida State University at a joint college in Tallahassee between Florida A&M University and Florida State University, where this is my research laboratory. So where I now, this is sort of a summary of the work that I've done. I did work on robots that walk on two legs. I had some fun projects on how to analyze how ostriches and other two-legged animals move, because we get a lot of inspiration from those animals in order to figure out how to control robots. Okay, some fun projects of trying to get robots to jump on sand. That was an interesting project because sand is actually very hard to model. Meaning it's hard to come up with good equations that describe how sand pushes back on a foot. And that makes it harder to actually control the robot. So that was an interesting project. And this kind of wacky robot here called Atreus, which could both walk and run. It was actually, it was a major project for my PhD for 5 years. Me and several PhD students had to make that work. So now I run my own laboratory called the Optimal Robotics Laboratory. This is a robot called Cassie. We now have a new robot called Digit. This is made by actually a couple of people from a company called Agility Robotics, which is a company started up by my friends and professor from my PhD program. They all went and started up a company in Oregon. Well, I went to become a professor, but at least I get their robots to play with and throw controllers on. But yeah, so Cassie is this sort of dynamic balancing robot that we work with. So today, I'll go over, the goal of today is to go over 2 different kinds of controller that built toward the current capabilities we have in legged robots. And I'll give you a little bit of history next, but the 2 things we're going to cover, one is the PID controller, and that was the full subject of the previous part that Dan and I covered. And the second is something we call the Raibert controller. It's named after Mark Raibert, who he in his lab invented and perfected in order to make robots hop around. And that was actually a really pivotal step toward getting robots that can balance on legs. Okay, so let's go through some of the history of humanoid robots. But before that, why humanoid robots at all? Why have robots that on legs? Why have legs at all? Well, the first answer you'll get from any engineer is because they're cool. I mean, I think deep down, we're in this business because we think it's awesome. I mean, because we all watch movies, sci-fi movies like everyone else. We think it's really neat. That's probably why we get into the field. Just like if you talk to probably a lot of paleontologists, some large number of them are inspired by Jurassic Park. Me, I was inspired by Johnny Five from Short Circuit. It's a whole story. But why legs? The more important question with why legs is like, why not wheels? Okay. Like, why not wheels? And because wheels are great when the ground is flat and everything is smooth. But when things are unpredictable and things go awry, sometimes it's good to have new contact points to make that are able to save you. Okay. And like, here's a guy who used his legs to save himself from a motor crash. Look at that. Crazy. He's fine. Spider-Man's okay. So, and when it comes to when we're studying legs, we actually learn we learn a lot of things. One is how we get robots to go up and down stairs. We generally speaking build our world around our capabilities, around us. We put stairs in our houses. If we have emergencies, like we have a fire, if we want to be able to send something in to go and rescue people inside, it'll be great if we didn't risk human lives to be able to rescue someone inside of a burning building that might have stairs and might have to go in and pick someone up and take someone out of the building. Can't really fly in a drone to pick up a person. They don't have good payload capacity. So that's one application. The other, which is people who have lost the ability to walk. This is and creating exoskeletons that allow people to walk. Like this is like a robotic exoskeleton that I'm mildly covering up with my face here. And so it's designed to basically walk someone around inside of it. Okay. And whenever we learn something about how to make a robot walk, we actually learn a lot about how to make people walk as well. So, and more generally, we are trying to take robots from along a trajectory from where they are now, which is largely in manufacturing, right? And in manufacturing, the environment is very, very tightly controlled, right? You know exactly who's in the plant at any time. The part that you want to pick up, you know where it's going to be, pretty dang close. It's very well controlled. But as we want to add more autonomy to robots, we want to be able to take them out to places that are less controlled. And that means putting them out into the field. I'm covering up a picture of a hiker, out in the, how we get a robot to hike out in the woods. And that means there's a lot more environmental uncertainty. And legs are really good when there's a lot of environmental uncertainty because you can always pick up your foot, pick it down, and put it down over things. So that's one of the reasons we want legs. So a brief history of legged locomotion and how we have and how we have approached it. There are largely two approaches that were taken, and we're going to talk about one of them today. But the two parallel tracks in the history of how we try to make robots walk, one is sort of a safety first approach, and one's an agility first approach. Okay, I'll give you some examples. So we'll start with the safety first approach here. Okay, so back in 1969, there was a paper that came out. It's called on something we call zero moment point, ZMP, zero moment point, and basically this paper came up with a very simple mathematical criterion for whether or not a robot was going to tip over. Because what's the biggest problem with legged robots? Probably that they're going to fall over. Right? And then they're going to break. It happens all the time. So this paper basically came up with a simple way of saying that, hey, in essence, if you have your center of gravity of your body over your foot, then you will never tip over. Okay? So if you can generate a gait, that's what we call, walking, it's like a gait, right? Then if you generate a gait where you always have your center of gravity over your foot, then you will never tip over. It's safe, theoretically, right? So if you build on top of that fundamental precept, you will never fall over. Okay. And so back in the 80s, Honda put a huge effort for decades, almost in secret for a long time, to develop humanoid robots that use this principle to be able to walk. And they did an incredible amount of research to be able to, behind the scenes, to make this happen. Look at all those different prototypes that they put together over all those years. Okay, and what they ended up with was this robot called ASIMO. ASIMO came out in the year 2000. Okay, it's an incredible robot. In my opinion, it should be the most famous robot in the history of mankind, because what they achieved, especially at the time that they had, is amazing. Like, the robot walks. The robot. They actually have it serving tea. They actually got it to run. It's really incredible. But one thing you'll notice is that whenever it's walking, it's always hovering its center of mass over its feet. And it's very gingerly in how you can see it's sort of like that, right? Okay. And that means it's actually not particularly agile for the most part, but it's very safe. So that became the standard for how you control robots for a long time. And people then found ways to extend this method. There's very famous papers, and so here's a robot that they have doing a dance routine. This HRP-4C robot, they have doing a dance routine. Nowadays, there are all kinds of robot dance routines. But just if you see cool robot videos from the last year or so, oh, look at this cool dance, make sure you go back and compare it to things that were going on 15 to 20 to 25 years ago. You might be surprised what people were doing for a while. But yeah, so moving on though. So they got ASIMO to run. This is so impressive. I was a grad student at the time when this happened. I was like, I can't believe they got this robot to run as fast as it did. Very impressive. In fact, the way it runs is kind of interesting. It's going to be very different from the way that it runs, that the robot, the controller we're going to be doing today runs, for reasons that I might be able to explain later, but I'll keep moving along. So that's a safety first approach. And a lot of robots, even to this day, use this safety first approach with this zero moment point, hover your center of mass over your foot approach. But then at the same time as that was being developed, this agility first approach was also being developed. Okay. And it really goes back to this guy and all of his students named Mark Raibert. Okay. He was at Carnegie Mellon and then at MIT. He had what was called the Leg Lab. He was an academic and he created the Leg Lab. He's standing there next to one of his hopping robots. Okay. And he had the idea that making a humanoid robot with all of these joints and making it walk, there's a lot of complexities to that you can actually circumvent, you can get around by making a much simpler robot. And instead of trying to walk, trying to run first. It's kind of counterintuitive, running before you walk. And this is in the 80s. Okay. And here's what he's able to do. He and his team. Okay. So look, this is a robot. It's got a pneumatic little plunger in its one leg. Okay. So basically the air compresses when it hits the ground. So it's a little bit like a spring. Okay. And it's just hopping and hopping around. Look at that. And it's powered. Now, how is it powered? It's actually powered by a big pneumatic compressor pump in another room. And they did multiple versions of these robots over the years. And this is a 2D one. You can see that you got it to go faster. This is a two-legged one. You can see that these things are going pretty fast. They're pretty agile, right? And yet they don't fall over. They have a way of remaining stable, not falling over, in spite of the fact that they are not hovering over a foot, right? It's an agility first approach. Okay. And they call these the Raibert hoppers. They're very famous in the world of legged robotics because named after Mark Raibert, of course. Now, his students, there are many of his students, contributed a lot to these. It's actually funny. I actually have an attachment to Mark Raibert because my PhD advisor made the robots do the flip, and whose PhD advisor was Mark Raibert. So Mark Raibert's my great granddaddy in academic terms. So these are different robots. There's the spring flamingo right there. They're all similar and related. Okay. But one thing that Mark Raibert then went on to do was found a company called Boston Dynamics. He's the chairman of the company. And so this robot Big Dog, okay, which hugely famous, came out of Boston Dynamics and Mark Raibert's leg labs. They started a company. Okay. And the way that this robot is able to it's designed to be a robot pack mule. Okay, it was funded by the U.S. Defense Department to be a robot pack mule, but this is the kick seen around the world in robotic circles. And you might say that's a quadruped. That has two legs versus one leg, but it actually uses a lot of the same control principles that Mark Raibert put into his first hoppers. Okay, one thing that's super clear is that when it gets kicked, which we're not allowed to kick robots anymore, apparently it's not cool anymore, so we don't do that anymore. But it puts its leg out. Watch, it's going to put its leg out really far, right? Leg out really far, right? Very, very simple idea that if you're moving to the side, you put out your leg to catch yourself. Very simple. We're going to code that idea up today. And this applies to bipeds as well. This is a robot called Petman, also developed by Boston Dynamics, walking on a treadmill. It's using, we don't know exactly what it's using because it's proprietary, but we have a pretty good idea that it's using similar principles to the Raibert controller, where it's trying to put its foot out to catch itself in the right spot when it's falling from side to side. Because you notice, unlike when ASIMO is walking around, this thing is falling from step to step, okay, and catching itself. That's what walking really is, falling from side to side and catching yourself over and over again, all right? So you might wonder what that robot was developed for. This is another version of this robot in a chemical warfare suit. So sometimes people wonder where funding for humanoid robots comes from. It comes from all kinds of weird places. So this is what basically there was an obscure law in the United States that if you wanted to test a chemical warfare suit, you had to test it with a real chemical warfare agent. And they didn't want to do that with a real person inside of the inside of the suit. So they funded Boston Dynamics to make a robot that would test them. So that's what this is, but it's using similar controllers. So it's pretty wild. Later on, people came up with the idea of developing. So later on, Boston Dynamics then created a new version of the robot called Atlas. There are several versions that I'm skipping over, and the methods for controlling it become more and more sophisticated. But down at some level, there is some element of those original Raibert controllers baked into this. And Boston Dynamics is not the only lab that's inspired by these controllers. There are many, many others. Okay. And I think what really became famous here is when you had Atlas. This is like another level right here. They're doing some really sophisticated control methods here to make Atlas do all these cool parkour maneuvers. Incredible stuff. And the field continues to move forward. I mean, I need to update this presentation again with all the cool acrobatics that all these other companies like Unitree Robotics are doing. But for the sake of time, we'll keep moving forward. All right. It's because there's so many other humanoid robot companies out there. This was as of 2023. And my goodness, there are probably 100 startups now. Incredible for humanoid robots. So, but what we'll be learning today is controllers for the Raibert hoppers, okay, and how they work. Okay. And that's what our goal is going to be, because we're going to cover these two topics, one of which is the PID controller. One is the Raibert controller. All right. Which uses PID as part of it. Okay. And one thing I want people to keep in mind as we're doing that is that while there are more sophisticated computational approaches for legged robots that have emerged over the years, and there certainly are, I'll show you a few examples. This is one that I know really well because I was a part of this project, where we had this walking robot here, this massive 260 pound robot called Duris that we wanted to do control of. So we used this massive optimization to optimize the motion of all of these of all the joints here to come up with an efficient walking gait. And we put it on a robot, and it walked. Well, it almost walked. Okay, we basically put that optimized trajectory on the robot, that this optimization that we came up with, but it wasn't quite stable enough. So what did we do? We added a little bit of we added a little bit of Raibert smarts to it. Okay, that when we're being pushed to the side, just kick out your leg a little bit more. That's it. If you need, and there are other elements to the controller as well, we'll get into, but we use a little bit of that Raibert smarts to stabilize it. And this was many years later. Okay, and this also applies to things like deep reinforcement learning. And people have heard of deep learning. You know, it's an incredible advance that we've been taking advantage of. Here's let me scoot through a few of these things here. Let's see here. This is the robot Cassie, but not my lab. This is my former lab at Oregon State. They've really embraced deep reinforcement learning and got Cassie to set a record for the 100-meter dash. They eventually ran a 5K with this robot using deep reinforcement learning. But down at the core of these controllers is still a PID controller. All right. So I want people to know that there's still applicability to these things, even in the most recent of robot capabilities. So with that, let's go to the board. All right. So here we go. So let's explain a little bit of our two topics here. What's today here? Today is 2025, 08, 23. Okay, we're doing PID and Raibert hoppers. Raibert controllers. Okay. So the PID controller is an incredible tool. I mean, you can't do robotics without it, and robot control without it. And it existed long before robots. Okay, so one thing I want to convey to people is that when you think of robot controllers, you probably think of code, right? And so you might think of, oh, write these lines of code, do this thing, and we will be writing lines of code today. But fundamentally, control is often seen as the discipline of mathematics. Okay, and more of a concept. Okay, so if we're drawing out what a controller is, what we'll often do is we'll say, hey, here's something that we want, something that's desired, and we will draw a little diagram that looks like this, where we say, oh, here's desired, here's a controller, here is our robot, and here is our output. And then we will loop it back, okay? This thing, we call this a control block diagram. This is how we often think of controllers, all right? And the idea is that you will often have something you want, right? And we'll do some simple examples with just me waving my hands around, okay? Let's just say I'm trying to control the torque at my wrist right here, okay? To move it up to this in order to move the pen this point straight up. Okay, my desired position is straight up, but my actual output might be over here somewhere. Okay, so what this does is it says, hey, our actual position is over there. Our desired position is up there. And we subtract these two things from each other. We take a positive desired, we subtract out the output that we actually have. And the result is something we call the error. Okay? And we measure that error and we say, okay, if we are exactly where we want to be, that error is 0. Okay? And that error is 0, and that's awesome. And that means that we send that signal into our controller, and if the error is 0, the controller probably doesn't do anything. It's done. Great, awesome, cool, right? And then we send some signal to the robot, and this could be a torque to the motors, right? And you just repeat this process over and over and over again, okay? You just you do that in a loop, right? And this controller, what does that look like? Well, let's give a sort of a physical example, okay? This can be very simple. So let's go back to my pen example. Let's say I want to get my pen straight up, all right? But it's actually right here. My angle is this, but I want it to be here. There's a difference between these two things. And I'm applying a torque at my arm to move it. What if I applied a torque to my arm that was proportional to that error, to that difference? So that means if I'm right where I want to be, then I don't do anything. My torque is 0. That works. That's pretty cool. If I'm over here, I start to apply a torque that's going to try to fight and pull me back, right? If I go even further, it'll fight even more and try to pull me back. Or if I go in the opposite direction, I'm over here, it'll try to fight me in the other direction, all right? This sort of proportion that we have an effort that's proportional to our error. So often we will write a control law that might look like this. And so a lot of times you'll see in control, U will be the variable for some control effort. We'll call that effort here. Okay. Is going to be equal to your error, which I'll write more as your actual minus your desired value. Call that the error. And it's multiplied by some constant. We'll call it K. And that constant K has a name called a gain. All right. This is a controller that says, hey, whatever my effort that I want to put toward my motor is going to be, it's going to be proportional to that error. Okay. So as a result, this is called a proportional controller. And it is just paramount to control. And the beautiful thing is that this value K, who gets to choose that? We do. And what does it mean to choose that number? What is the effect of choosing that number? Well, let's think about this physically for a second here. So if I have a force on my elbow that's pulling me back to the vertical, and it's proportional to how far I am away, that's kind of like a physical device. How that feels? That's going to feel like you're pulling on a spring. Okay? And the more I pull myself, the more I'm going to fight to come back, right? So it's actually like a spring. And if you know anything about physics, if you have a spring constant for a Hookean spring, a spring with Hooke's law, that K, that value K we're talking about, the bigger that is, the stiffer and tighter that spring is. And the smaller it is, the looser it is. And please make it a positive number. Otherwise, you will invent energy out of nowhere, and that's bad, and it'll go unstable, right? This is called a proportional controller. Or or P controller if you're nasty. Okay? P controller. All right? So, proportional controller. Now, funny thing about springs is they tend to go wonkety wonk, springety spring, splongety splong. They oscillate, right? So a lot of the time, if you were to put this controller on a system like this and you activate it, it will go wah, 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 wah. It'll overshoot and oscillate. Okay, when you want it to just come to rest where you want it to go. And so what people often do is they say, okay, well, a spring will try to pull you to where you want to go, but it won't stop you. But a device that will stop you is a damper or a dash pot is what people might call it. Sorry, here. So imagine that here is my hand. I'm applying a torque here, some control effort U, okay? And I have some angle I want to hit. This is my desired. This is my actual angle, right? So this torque, you can imagine it being like a spring between where I want to be and where I am. And a damper is often drawn like this. Sorry, it's a little sloppy. And the idea is that while a spring is proportional in force to how much you stretch it, a damper is proportional to the speed at which it's squishing, and it fights it, right? So if you've ever seen a door that has up in the corner by the hinge this little mechanism that slows it down, that's a damper, okay? And the faster you try to slide it shut, the more it fights it, right? So that's a damper. So what if we put a damper into this controller in addition to a spring? Okay, well, we can do that. So basically we would have U is equal to K desired minus actual. Is that right? I should have said desired minus actual. I screwed up a bit there. Technically it should be desired minus actual. Flip those around here. Desired minus actual. This is your proportional term, P. Now, let's add another term, which is another force on this that we're adding onto our controller. It's going to be the desired speed minus the actual speed. Or specifically the velocity, so you get it in different directions, right? And it's multiplied by, you probably can't see that. I'll move it a second. There we go. And it's multiplied by another constant. Well, we've already used K. So what we do is add subscripts. We said this is KP. We say that's KD. All right? KD for the derivative. This is the calculus term. I'm sure many of you have some exposure to calculus. But the idea is that this would be the actual desired position, the actual position, or the actual value. And this would be, the speed is the time derivative of position. So it will be the derivative gain. So this is a P, and this is a D. D controller. So this is called a PD controller, proportional derivative. Okay. And the idea is that this KD determines how stiff that damper is. The higher that KD is, the more it's going to slow you down, right? And so if you add KD, you raise that KD, if your system is springing around, the more you raise that D, the more it's going to want to slow down faster. And if you hit a critical value, it'll just go, woo, and come to a stop, right? Okay. That's a PD controller. And then we also added, we can talk about the I controller, which is the integral controller, which just to scoot through this idea is that, so I'll just write it out in full here, that you have some U is equal to KP times your error E plus KI, which is the integral of error dt. In fact, I'll include my of t's in here just to be a little bit better in terms of my math, just so it's correct in the end here. This is what a PID controller is. KD. And it's the derivative of E of t dt, where E of t is your error. That's your desired minus your actual. So these are all, that's your PID controller. And in essence, for certain kinds of systems, a lot of different kinds of systems, if you choose the right KP, the right KI, and the right KD, you'll be able to stabilize your system to some value and drive this error to zero. In fact, you can think of controls in general as a lot of the time just the art and science of driving a number to zero. Can you guarantee it'll drive this number to zero? Can you make sure it never gets too far from zero? It's sort of the math of zero here, okay? All right, so I'll keep scooting along here, Dan. I know we're kind of pushing time here. So we just need to make sure we have that under, so the PID controller is important, and we apply this to robot joints all the time. How do we get a robot to go to a certain joint? But what about the hopping controller? Okay. And this is where the art of Raibert comes into play. is because while this PID controller can work, there's no guarantee it'll work for a lot of different kinds of systems. So it's a bit of an art for deciding what you're actually trying to control. So the way that Raibert looked at this big problem, which is how do you stabilize a robot that's agile, is he said, okay, let's try to use PID controllers to regulate, to try to stabilize 3 different things for hopping. Okay, so we're gonna draw our little hopping robot here. And the way he envisioned it was that he had some kind of spring attached to a body, which was at some body angle theta. You got some leg angle alpha here. Okay, so in this whole thing, imagine it's moving like this. It's going, boing, 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 like that, right? That there were 3 things that you wanted to try to that you want to try to control. One is your hopping height. Specifically at the apex. Okay, so at the top of some hopping height. So imagine you're going like this. Woo, that's the apex, right? 2, you wanted to regulate your speed. Okay, and 3, you want to regulate what we call your posture. Now, the posture, what I'm referring to, is the angle of the body, that you're not flopping too far forward or flopping too far back. But those 3 things that you can regulate, and he found 3 different PID controllers that could help you stabilize those 3 things. And it's very easy to demonstrate. It's easier to demonstrate this in 2D in the plane. So right now we're going to deal with, here's X and here's Z. You're probably saying, hey, Christian, why not Y? Well, in legged locomotion, we often see Y is into the board and Z is opposite direction of gravity. But we often do this in 2D, but it can be extended to 3D, as you saw in some of those videos, right? So here's the ways that he applied a PD controller. So what he said is like, hey, this effort that I'm going to apply to my robot is not going to be a torque. What it is it's going to be when I'm on the ground. Let's say I'm just hopping straight up and down here, and I'm on the ground here, and I want to be able to hop to a higher height. What I will do is I will push on this spring, make it longer, like you're pushing down on a pogo stick, and that will be my effort. Okay, so if a spring has a rest length, every spring has a rest length that if you stretch it beyond there, it'll be tension. If you compress it beyond there, it'll push back out, right? Call that L0, okay? Plus some delta L, some change in L, okay? That right there, that's going to be the pushing effort. Okay? All right? So that's the pushing effort. And what he said is that that our error in height is going to be our desired minus our actual, right? The same thing. It's all apex height. And we will extend our leg at the bottom of the trajectory, meaning right there, right? Once we're at the bottom, extend, push. And that's what he does. So and how much we extend it is using a PID controller, okay? So that's controller 1. Controller 1 up here, where is it? You regulate hopping height by how much you push. Same thing with speed. He says it's just a little bit different. Is that when you're at the apex and you measure, when you're at your apex, you measure what your hopping height is. Okay, you measure you measure your hopping height, but also your speed. If your speed is too high, you kick your leg out further forward in a way that's proportional to how your speed error. So you have an error in speed, and you apply a PID controller to that, and that changes what this leg angle alpha is going to be when you're in the air the next time. Okay, and if you're too slow, it'll pull back the leg. And as a result, when it lands, it's going to actually kind of like, it's going to land and kind of scoot forward more. Whereas if it's too fast, it's going to push the leg out further and it's going to go boing and like try to slow itself down. Very simple. So, and for posture, it's pretty similar too, is that when you're in the air, you measure, hey, was I too far forward or too far? Am I leaning forward or leaning backward? And if I'm leaning backward too much, I will apply a torque in a certain direction. If I'm leaning backward if I'm leaning forward, I apply it in the other direction using a PID controller. So the key insight by Mark Raibert was that to regulate hopping height, you have a PID on push. For speed, you have a PID on leg angle. I bet. And I doubt we'll get to this today, but for posture, you have a PID on leg torque. All right. And that's it. Went a little further and longer than I wanted, but that's everything, Dan. that's that enough to go with?
Yeah, that's amazing. Oh, I'm muted. Oh no, I'm not muted. You can hear me. Yes. No, that's amazing. So, this is fantastic. So actually, you sent me a lot of information, and I've been kind of like, and you're frozen for me. So, oh no, you're not. Okay, maybe you were just like.
No, I'm just very still. I'm very still.
Wow, that was excellent work there, being still. You sent me a lot of information about how this works to look at in advance, and I think I kind of got it. And now, watching intently in your presentation, it's really starting to come into focus. So the next thing I want to do is kind of get started with some code examples and see if we can together start to implement those formulas essentially for the controller into the code. But I wanted to, a couple interesting questions came up during your presentation from the chat, and I also just wanted to sort of point out a couple things also to connect the dots between the sort of theory behind what Christian is explaining to us and how I'm going to implement the physics and drawing from the Nature of Code book and examples, which I'll talk about in a second. So let me pull up some of these questions onto the screen. Some of these are kind of going back, but this is kind of interesting, highly relevant to what we're about to do. So Teramushi asks, how often, so for an actual physical robot, are the controls being pulled, updated, sent each second? Is obviously in a animated simulation, we have this concept of a frame rate. We can think about time in different ways. How does that work in physical reality?
Great question. So in physical reality, the standard for a humanoid robot now is that if you want a quote unquote good control, you want to update at a kilohertz. Okay, for that, which now, I have my own opinions about that. That is definitely practically true with the methods that we're using. At the same time, some methods have been able to push it down to a few hundred hertz. And, but that's because the way that we're doing the calculations are probably like they're really tight. And, but I think that, but if you contrast that to people, I mean, if you pricked my foot, I would not be able to react to that for about 100 milliseconds. And yet I run just fine. Right? So it's one of the things that I look at as a researcher. I'm like, oh, there's definitely better ways to do it. But a kilohertz is like the standard. You probably get away with 500. But that's for modern controllers. For the Raibert controller, because it's so simple and you only have to push off at the right time and you make sort of smart decisions, I mean, you're probably talking 10 hertz on the order of 10 hertz range, and you get away with it.
Great, thank you. Another question here Specifically about ASIMO, did ASIMO scan his environment? Did the surface have to be flat? How did today's robots handle this? And also, like, this question came up for me as you were talking for the Raibert, even the simple, just like one-legged hopper. How is it detecting its apex height? There are additional sensors built in. To what extent do these robots, go full-on self-driving car with like, massive LiDAR scan of their environment versus they're just operating in much more simple ways to run down a track?
Well, it depends on the robot. For ASIMO, it was very clearly it was predefined. It was a predefined terrain, so it wasn't like rough terrain. ASIMO's control would not have worked well on super rough terrain. Although there are examples of it having little moguls on the ground that it was able to handle. But it's not like that wasn't able to like run up hills, and it was able to walk upstairs, but it had to know where the stairs were. And I don't remember how much that was vision-based versus what we'll often do just to show the locomotion is we just tell it, hey, the stairs are a meter in front of you, go. Because we're trying to show the locomotion, not necessarily the sensing. But these days, perception-based locomotion is becoming a hotter topic. There are approaches that people, of course, scan the environment and walk around. They absolutely exist. But there's a whole field of locomotion where they try to get away with no vision. In fact, just the other week, there was the humanoid robot games in China, and where they had sort of an obstacle course for robots, and they were using and some of the winning approaches use the blind approach, where they just had a stable enough algorithm that if they tripped over something, they just kept tripping over things and kept catching themselves. That's still a popular approach, but perception-based methods do exist.
I mean, great. So that's really interesting. So, the reason why I asked that, and also I think, to segue into kind of what I want to talk about next here, and let me move this comment off the screen. And actually, 2 people commented about this during your presentation. One comment came in, this reminds me of the video, Arrive, Steering Behavior, Dash Nature of Code. Okay, that's a video I have on my channel. Another comment came in here, similar to how like a particle in a P5JS sketch kind of simulation follows the mouse, right? Acceleration, how is acceleration, velocity, how are those tied to this concept of error? And actually, so I don't know if we talked about this before, and this is going to kind of bring us into the code, and I don't mean to be overly plugging my Nature of Code book, but
it's your screen,
certainly
dude.
this is a primary sort of like foundation of many of the examples and topics I cover on the channel. Now, Christian, are you familiar with a book called, let me see if I can find it in here, Vehicles by Valentino Breitenberg, the concept of the Breitenberg vehicle. Okay, you will be interested in this, and I've just spelled it wrong. But there's a book by Italian cyberneticist Valentino Breitenberg. I believe it's from the 1980s, which we can kind of zoom in here and sort of see, which creates these. The book is sort of like a work of science fiction in a way, theorizing about these sort of simple, dare I say, robots, creatures, whatever you want to call them. He calls them vehicles that have simple sensors and actuators that define how they move. And they might be expressing like fear by like moving away from the light, or love by moving towards light. It's a fascinating book. So I would highly recommend it, but it serves as the foundation for the work of Craig Reynolds, who is, and I'm just going to come up here, and this is the paper that I constantly refer to. Let's see if the internet will comply here and pull this up. But Craig Reynolds was was working at Sony back in the 80s and 90s and developing all these algorithms for animation. So how to control autonomously a character inside of an animation. I don't know why this isn't coming up here, but I'll just go to my section about this. And I'm referring to it here. And one of his key formula, and so his key formula, and I'm going to look for it here, is this. The steering force is equal or proportional to the desired velocity, and I mean both the speed and direction of a given character, minus the current velocity. And this is exactly the same formula that you've seen in Christian's lecture. Now, and so what's exciting about this is we have a model for this already, and we have a code library that I can apply the sort of vector math to. And what you'll see is that this leads me to do the sort of canonical example of this. And again, the internet is being a little bit wonky here, but this came up, is this idea of controlling this character to follow this dot. And so where you see this in the vehicle's code is right here in this seek function where we look. The desired velocity is a velocity that goes at maximum speed directly from the position to the target. But the steering force that we're going to apply, proportionally according to its maximum ability to steer, is the desired velocity minus its current velocity. Apply that, and we get this result. And we can see all sorts of, I've kind of gone over this countless times on the channel and other videos. And of course, I have a whole chapter that goes through this. So I think, one, it's really interesting to connect the dots here. And on some level, what we're building is a more sophisticated controller for some of these autonomous agents that I have trying to perform different kinds of tasks. And just to this will lead to all sorts of, I'm trying to see if I can pull up a more interesting example, but eventually, we can start to build systems like this, where these creatures both desire to follow this path as well as not to run into each other. So I'm just, I'm kind of excited, we're going to be here for a little less than an hour. We're not going to get too far into this, but there's so many connections that I think I could draw on and further explore between some of this material. The other thing that I want to mention, I'm really fascinated by this concept of sensing the world and also different algorithms for control. The Nature of Code book ends on this idea with these creatures that can sort of sense things in their environment and make decisions about how they move. So that's, I don't want to get too far off in that, but that was where I wanted to ask you this question, because for me, what I do with these systems, and if we go all the way to the end, there's an example of these creatures kind of learning to sense where the food is and stop and eat the food. And so even though they're using a neural network behind the scenes, ultimately, they are just tuning values for the steering forces. And I think maybe, so this is my question for you, is this kind of the same as what you were talking about? The Cassie robot might be using deep learning to control it, but what it's ultimately doing is maybe, I'm sort of speculating here, using deep learning to optimize and tune the weights, if you will, of the P, I, and D of a controller. Is that a way to, is that somewhat accurate?
Yeah, if you could put me back on the full screen, I can show you. It's pretty close to it. It's pretty close to it. So yeah, so typically the gains are already kind of pre-selected based upon the joint. They kind of have a good idea for what the gains are. What the neural network is telling it is at any given moment, what is the desired angle of each and every one of the joints? That's what allows it to kick forward, put the foot down. So it's coming up with what is that desired position for each of the joints before it goes in. That's what it's doing.
Yeah, that makes total sense. And actually, I have some examples where I'm applying this evolutionary genetic neuroevolution algorithm, which is using a genetic algorithm to evolve the weights of a neural network to control the steering force. But actually, to do that, what it's doing is it's picking the desired velocity to steer towards the target of the food. So anyway, more things to come. And actually, I've never done a proper simulation of the Braitenberg vehicles. They are the sort of foundation for a lot of my examples. But that could be an interesting topic to explore in the future on the channel. And I know I've seen some YouTube videos where people have built, the Braitenberg vehicles are sort of a thought experiment, but I've seen examples of people building simple, physical versions of the robots, basically, that are following the Braitenberg rules. So that could be also another point of something to collaborate or think about in the future. But let's move on to the P5 code. So there were three things that Christian referred to. There's the tuning for the desired apex height. There's the tuning for the desired speed in 2 dimensions. And then there's the tuning for the posture, which is kind of, I guess I would characterize as the sort of angle of rotation of the body of the robot. So I can say for now that we're definitely not going to get to the posture, and I'll tell you why for a second. Let me go back to the nature of code, because there's a sort of core question here in terms of, we're not building a physical robot, we're building a simulation. So, by the nature of a simulation, we have to make certain simplifications and assumptions for how we're going to implement that. And last time, and I closed this sketch down, but last time we did our PID controller with the cart pole, we actually used this physics engine, which I have here in chapter 6 called matter.js, which allows you to do, and I'm sorry for the completely insane scrolling here, but basically it allows you to create simulations like this with rigid body mechanics. And so there's a lot of value, I think, in using matter.js, and ultimately, I think maybe there's a version of what we're doing today that would benefit from using matter.js. But I think learning-wise and trying to understand the algorithm, there's a lot of additional complexity with adding this whole physics engine, as well as we're kind of losing control of manipulating the spring force and this damping force, the dashpot force ourselves, to understand how the system is working. So for today, what I'm going to do is go backwards and build upon the spring example that I have in Nature of Code. So we're going to start with that. So, I'm jumping, so, people are coming to the stream from all sorts of places, but just to, apologies for some of the concepts that might not be familiar to you. We'll try to keep things as beginner friendly and explain as much as I can as we write the code. But what I'll just sort of quickly say is, what the chapters, what the material that is being, that is sort of the prerequisite for what we're doing is kind of understanding the concept of a vector as a, oh boy, I've spent my life trying to define a vector, and I've lost the words for it all. Christian, save me here. How would you define a vector?
So, I mean, a vector is just a tip and a tail.
Yeah,
it's an arrow in space, in some dimensional space that starts at an origin and points elsewhere.
Yeah, exactly. And so the position of an object on the screen can be defined as a vector pointing from the origin to where it exists. The velocity of an object on the screen, a shape on the screen, can be defined as its, the directions from point A to point B, acceleration is a vector. So this is a sort of core concept. And of course, this idea of a force, and I'm looking for a diagram here, this idea of a force being a vector. And one thing that's going to trip us up, I'm just warning everybody in advance. P5 canvas, computer graphics window, Y points down, not up.
Down,
so,
down.
So we're going to have to kind of keep track of that. But you can see here a gravity force is a vector. That force can be applied to an object. So this is where we're starting. So I'm going to go back here, and I'm going to click on spring forces and just kind of give you a quick review. I'm just going to, rather than go to the whiteboard, I'm just going to quickly give you a quick review of the concept of a spring using some of these diagrams. So the idea of a spring, we can think of a spring as a bob, this particle, and this is where there's no rigid body physics, there's no rotational dynamics here. This is a single point mass. Basically, it's just a point that has some mass to it that is attached with a spring to an anchor, which is up there at the top. A spring has a rest length, which is the length at which there would be no force applied because it's at rest. If you were to extend the spring, if I were to pull it down to this current length, we measure the difference between the current length and the rest length. That could be called X in sort of mathematical notation. I think I refer to it as the stretch. A stretch could be negative, though. It could be compressed. And there we go. The force of the spring is directly proportional to the extension of the spring. And what you'll see here is that my code example has a class for the bob to keep track of the bob's position, velocity, and acceleration. And the spring class keeps track of the anchor position. The rest length calculates that spring force. And what we have is this example. So this is the sort of beginning example where I can click with the mouse. I pull the spring. Pull the spring, we see it sort of snap back and sort of bounce. And there is a damping going on here, but it is not, in my nature of code examples, I didn't actually implement the proper dashpot damping. It's just sort of like continuous, almost like air resistance that exists in any of the systems. So what I was thinking about doing, but I'm going to skip ahead for time, was taking this exact example and adding some things to it. But luckily, I've already done that. So what I want to do here is look at this code example. It doesn't have the PID controller, but it has a few extra things that I'm going to talk you through. And then after I talk you through that, I'm going to ask Christian to help me step through and start adding what we need for the PID controller. And okay, so let's look at a couple things. First, let me just run this. And I'm gonna, again, I'm pulling on the spring, which is not something that's gonna happen with the control system. It's gonna, it's going to work on its own, but so I can pull on the spring and I can pull it like this. So the first thing I want to just point out is in this spring class, I have added this damping force. So first, let's just look briefly at the spring force calculation and I meant to rename anchor to foot because it's kind of like the bob is really the body and the anchor is really the foot of the robot, but I won't worry about renaming things right now. Maybe after the stream is over, I might clean some things up to release the code with different names. But we can see here that we're calculating the spring force as a vector that points from the anchor to the bob's position. The stretch is the difference between the length of that vector, the magnitude, minus the rest length. And then the force's magnitude is the spring constant K, the springiness or the stiffness of the spring, times that stretch. This is Hooke's law right there. I didn't show that diagram in the Nature of Code book, but that's Hooke's law. Negative K times X. We apply that spring force to the bob. So this is everything. You could read the chapter. You could watch my videos where I go through and build this example. This is the new part. So the new part here is to add this damping force. By the way, I'm always stuck, and I went down a rabbit hole of whether it's damping or dampening is right. And it's damping, because dampening is getting something wet, right?
Exactly. No, okay. I yell at my students. I'm sorry. I mean, I'm very polite to my students and tell them it's not dampening. Because
right.
That I would deduct points to say dampening.
Yeah, okay. Well, I would have gotten like a B+ in your class many years ago because I was saying dampening way too much. Damping is right. Okay, so the damping force is in the direction, or the negative direction, we'll see, of the spring force, right? It's in the opposite direction of the spring force. So to get the direction of the force, we just need to copy that spring force and normalize it because it's not the magnitude, right? Does anybody remember this? Nobody can really answer. You could answer this in the chat. But think to yourself, do you remember what was the magnitude of the damping force applied to? It wasn't related to the stretch. It's not related to other things. It's related to the velocity. So we first have to normalize that force, and then we have to calculate the magnitude. Now, this is some funny business going on here that might not be immediate to some of you watching, even if you're just on chapter 3 of the Nature of Code, because I haven't covered in chapter 3, I don't cover the dot product yet. But basically, this is using scalar projection. And if I go here, and we're going to get to the Raibert controller, but if I go back to autonomous agents and my path following section, I have a diagram here that I want to pull up. One of the things that I need to do in path following is find the point on a path relative to where this vehicle is going in order to understand where it needs to steer back to the path. And the technique for doing that is with this algorithm called scalar projection, where I'm essentially taking the vector A and projecting it onto vector B. So in our case, B is the spring force and A is the velocity. I want to know we're going to do a 1D controller, so this doesn't actually matter because everything's just pointing in one direction. So it's just the raw speed. But if I weren't in 1D, I want to know the amount of the velocity relative to the way the spring is moving, and that can be done. You can read this section to see how this ultimately. I explain how this comes down to using the dot product, and here's a different diagram. So long story short, I'm able to set the magnitude of the damping force according to the amount of velocity in the direction of the spring force times another constant. I guess, does this constant have a name? I guess it's the damping constant, the dashpot constant.
The damping coefficient is
coefficient,
right?
What we typically
call it.
Yes, right. And then I apply that force. So that's what you're seeing here in terms of me pulling on the spring and having it slowly come to rest, which it'll work differently once it's actually hopping. Okay, that's one thing I've added to this. The other thing that I've added to this, which really should be like, if I ever do a Nature of Code 3rd edition, got to add a whole section about this, is you're going to see something you very, very rarely see in my code, which is DT. So the delta time. And when I talk about time, I'm talking about frames of animation. In other words, I make an oversimplification. I talk a lot about this concept of Euler integration, which is right here. The Euler integration, the main physics algorithm, is acceleration is added to velocity, velocity is added to position. This is what we do. We update every frame. And in every example, if I go to, I'm just going to show you, just really getting to the end of this brief discussion here. If I go back to, where's the sketch? If I open this and go to here, we can see this is what you'll usually see, and this is the simplified damping that I do. Let me take that out. Right? Acceleration just goes into velocity. Velocity goes into position. One mathematical update of the physics equals one frame of animation. But there is so much lost in having big time steps. And a lot of times, and in most cases of like creative coding and making like a animation project, that loss doesn't really matter. The system behaves in a perfectly fun and adequate way. But for what we're doing here, it can become unstable if you're really trying to tune the parameters in a more precise way. So what I've seen here, take a look, freeze your memory on this, because the vector code in JavaScript always looks a little wonky. What I'm actually doing here in this example is, instead of adding the acceleration directly to the velocity and the velocity directly in the position, I'm adding a smaller amount of it. In this case, like 1/10 of the amount, because I'm going to do it 10 times every cycle through draw for every step of animation. So that's one thing that's been added to this. I have this concept of the number of steps. Like, I could put this at 1, right? This is what my Nature of Code examples do. And this still works just fine. The accuracy is a little less off, and if I were to kind of stretch it more, we might see it destabilize. And I could also do something like do it 1,000 times. And it looks the same, but it's taking, you can see it's actually applying the forces, applying the force of gravity, applying the force of the spring, and updating the bob. That's the only thing moving. The spring is massless. It doesn't exist. It doesn't receive any forces. It's just a force in the system in this case, applying it with that delta time. So this is something new that you might not have seen in my examples, which maybe would make sense for me to just do a whole video covering kind of how to do that, but I wanted to mention that here. So those are the only two things that are added. The other difference, of course, from this example is I put the anchor on the bottom. So the first thing we need to do, and Christian, this is where I think we're going to have some more collaboration here. I'm going to take out this mouse control. That is completely, and actually, let me duplicate the sketch. I'm going to duplicate the sketch, and I'm going to take out this mouse control, and I'm going to run it. So the first thing we need to do is figure out how we're going to make it hop. So my thought here is, I know the controller is figuring out how to adjust that delta rest length. So I was thinking that the first thing we would do is I would write a function where I click the mouse and it just arbitrarily resets the rest length to something shorter. And then we'll need to add in a detecting of phases so that we can know. The one thing that this isn't doing is the anchor shouldn't be pinned to the ground. The anchor, you can think about like the spring is compressed. As it's expanding, as soon as it hits that rest length, then if it's not pinned to the ground, it's going to jump and leave. So we need to detect when it should leave and then when it should hit the. So I wonder if we should do those two things, which in retrospect, maybe I should have added those things in advance so we could start with the controller. But I think there's some good learning there in figuring that out that's relevant to detecting the phases. So does that make sense?
Yeah. Makes total sense. Let's go with that.
Okay. So first thing I'm going to do is add, and you can see me coding right now, Christian, so that you can see the code. Okay, great. I'm going to add a quick mouse press function, and what I'm going to do in this mouse press function is we're just going to say spring.restlength, just going to hard code in a new value. So we gave it, right now it's got started with a value of 200, so let's give it a value of 100, which should mean as soon as I click the mouse, it like got a new rest length, and you can see it started to compress down, but because it's pinned, it is not going to leave. So that's the next thing we're going to do. What my brain tells me to do right now is to add a new property to the spring object. But I think for the sake of what we're doing here and where we're going with this, I think what I want to do is step away from kind of best practices and sort of object-oriented code organization and just put some raw stuff in this main sketch, the sort of setup and draw loop in order to detect these phases, because I think that's going to help us work through this step by step. Then I would obviously, I don't have my sound clip for the refactor song. We don't know. I would certainly want to refactor.
There's a refactor song?
Oh, yeah, many years ago, I would always talk about, so I would always say, oh, I'll just refactor this later. And then, of course, I would never do that. So a viewer made a song called I'll Refactor This Later, and I had a sound clip of it. I'll share it with you later. Okay, so let's just do, I'm going to do a phase state variable. And right now, I think we're going to keep it simple. I know we're going to have multiple phases, but maybe what I'll do is just say it's either in stance is 0. Wait, no.
Yep. And to be clear, Dan and I talked beforehand. Stance means when it's on the ground for the audience. So it's stance and flight is what we call
and
them.
one. So we're going to have to revise these. So I'm going to say that the phase is in stance, and when I click the mouse, what I need to do, and all of this is going to happen in these sub-steps. Like this is something that happens not once per frame of animation, but it happens, we need to check for this every time. So how would I detect if it should move to flight?
So the way we detect if we move to flight is we will check the position and whether or not the distance between the mass and the ground is greater than the rest length. If it's greater than the rest length, then that means that the spring would need to be in tension to stay attached to the ground, and because the ground isn't sucking down the foot, it'll just release and go into the air.
Right. Great. And since we're doing a 1D hopper right now, I'm going to write the code with 1D checks, meaning if I were doing this with vectors, I would look for distance with vector math and think about the sort of 2D relative positions of things. But just here, I could just say the Bob's Y position. Now, we have this funny thing. So let's make another variable, and I'm going to call it H, and I'm going to just call it capital H, even though I don't love that right now. I'm just going to use lowercase h. That's fine. I'm going to say H is the height of the window minus the Bob's Y position. That's its height, remember, because the Bob's Y position goes from 0 to height towards the bottom, so I've got it. So if height is greater than spring.rest length, then the phase state, I called it, should go to flight. Okay, so one thing I'm just going to do is just console log the phase state here, just so we see that. And I click the mouse. Okay, so it went to flight. It's never going to go back to anything else, but I just wanted to see that triggered. So that did trigger at a certain time. Now, what happens when that happens? So first of all, if it's in flight, the spring force no longer applies. reached its rest length and it takes off. So there's different ways I could approach this, but I'm going to just say if phase state is in stance, apply the spring forces. So let's try this. And what we should see now is, okay, now I must have gotten something, something is wrong with when it goes into flight. If H is, I think maybe, here's the thing. We need to know that it's moving up, right? The mouse, its position is bigger than the rest length because it's starting up high. So I also, in this case, and there might be a different way to approach this, but I want to just check that the velocity is moving upwards. So I want to check that it is moving upwards would be less than 0. Let's try this. Okay, there we go. Now it's going to come back at some point, and you can see the way that I'm drawing. So again, we have to tune this, but this is now at least getting into the flight state properly. And the other thing that I would say is if it's in flight, I'm going to do something kind of clunky here, but if it's in flight, I'm going to say the spring should fly. And I'm going to do this because I think what I want to do is I'm going to allow the anchor to move. Like, the one thing you have to realize, and this always comes up with doing a physics simulation, is there's what the things are actually doing and how you're drawing it. And sometimes you can get really tripped up because the math might be right, but you're like drawing it in a different way than the math, or vice versa. So I'm going to try to keep, and Christian, if you see me going in the wrong direction, please feel free to stop me.
You're doing fine. The one thing you're going to be aware of is that, so like if you're in flight, your foot is beneath the ground, you will fall through to the center of the earth. That's the one thing you probably might be encountering at that. And that's fine. We just deal with that. Like, that means we failed anyway, you know, to get the control.
Yes. I think we're going to be able to tune the values of the spring. Uh-oh, I lost Christian. It might be his internet. Oh, he's coming back. I've got you back. I lost you for a second there. It was some sort of glitch.
I don't know if it's going on with my connection or something, but I'm here.
Great. You're back. Okay. Okay, so now in spring.fly, what I'm going to write this function fly, and what I'm going to just do, and I'm going to do this in a hard-coded way. I'm going to say the anchor, its y position equals, and this is one of the things I don't love about the P5 web editor. When I have the auto refresh on, it'll switch position, y position plus the spring's rest length. So it's hit its rest length and it's flying. The anchor is just going to now be moving along with it. So let's just see if this does the proper hopping. Great. Okay. So now we just need to tune the stuff. The gravity is much too weak, right? And we don't have anything to detect when the anchor hits the ground. So that'll be our next. We gotta detect stance again. But let me at least increase the gravity. I'm gonna by quite a bit, and that was way too much. And also I might be like compressing the rest length by an extreme amount. Ooh, wait, okay. There we go. That was kind of a nice little like, I don't know why it's okay. Hold on. There we go. That looked right to me. Oh, I lost Christian again. He's gonna come back. Why is it sometimes, there we go, working? Okay. Here comes Christian. Hopefully, it might be me because I'm seeing some people in the chat were saying the internet troubles are me. This is not I think the internet troubles are me. So I'm sorry, everybody. They're not you, Christian, they're me. But hopefully, we're gonna keep going because regardless, we're recording this. So, and it will make it into the archive. Oh, I don't hear you though. Ooh.
That's me. That was me.
Okay, great. Okay. Chat, let me know if you're hearing and seeing us. I was wondering why there's so few messages in the chat, but hopefully they're gonna, you know what? I'm gonna just briefly pull up my YouTube dashboard just to see if it is. YouTube is not, yeah. Okay. So it's just, I'm sending I've got some low bandwidth right now, which is a little bit unfortunate, but people are saying I'm gonna plow forward. Okay. Back to here. Nope. Back to here. Okay. So what we need to do now is detect when we need to go back to stance. Okay, so in order to detect when I need to go back to stance, I would check the anchor position. Is less than or equal to the height. That's the floor. No, greater than or equal to. Then the phase state equals stance. And also, we pin it equal to the height. I think it's as simple as that. Okay. Okay, it didn't fly. Okay. It's because it never
start the height in the air and above the rest length, and maybe with the vertical velocity, then make sure it goes up and it comes down and lands and sticks.
Okay. Yes. Okay. That is a smart thing to do. Okay. So first of all, I'm going to change the rest length to 100, and I'm going to just give it a smaller compression. And okay, I think I'm also going to lower the frame rate so we can watch it a little bit more slowly. Okay, perfect. So the anchor, right, So one thing I need to do is the spring, when I create the spring, let me also, the Y position of the bob, and I can move this, I can give myself more space here. The Y position, the anchor is not, starting pin to the ground. Okay, there we go. Now what is going on with this first frame? That is so weird.
It looks like well, based upon the first frame, I would assume based upon does your heart height start at 0 and 0 is the top of the frame or something like that's my guess because
I know that. I mean, in one sense, like let's not worry about it because oh, you know what it is? It's the first time I draw it, it hasn't cycled through any of the physics. So I mean. So you would never really notice this, but I'll draw the stuff after like the physics begin. There we go. Okay, so this is good, and it's going to compress, and it's going to go up, but it's getting stuck. Yeah.
Well, the question is it going back above the rest length? So maybe if you got rid of the damping temporarily, if it's perfectly energetically conservative, it should keep bouncing. So let's try that.
Yeah. Okay. Good call. And I've got a low frame rate just to, okay, no. Okay, so let's see, what did we miss? And I'll check out the, okay. If height is greater than spring rest length and bob velocity, so let's console log these things.
Yeah, that'd be great.
And, look at these as we go. So we're going to be looking at the height, the rest length. So
the rest length is what, by the way?
Oh, it's 100. I got above. Oh, but yeah, okay.
Yeah, it's going back above 100.
I think it's going into flight, but it is going right into stance immediately. Like, let's take this out again. Because I think it's, it hasn't,
this I could be completely off base on this, Dan. But like the way you're defining height, I mean, I'm not familiar with how your code defines height. I know you say it starts from the top of this frame is 0, increases down to the bottom. Greater than or equal to height, wouldn't that be if it's and if the height is and if the Y anchor is I'm sorry, is it defined from the top of the frame or is it defined from the ground as
so
0?
The ground is pixel 400. So basically how high it is off the ground is 400 minus its, if its Y position is 350, then it's 50 pixels off the ground.
Okay. So can we so it stays in stance, but clearly it's let's go back to the situation where it wouldn't, where it bounces, but it wouldn't take off again. Let's look at the console.
Right.
Again.
So so I think the issue is that I wonder if I take I know this is let me just, I think the issue is that it is, I should really also do the, let me do the let me log the phase state as well.
Yeah, that'd be perfect. So that way we guarantee that it does it. So one is stance or one is flight?
I forgot already. One is flight. So it's in flight.
Okay, then it goes into stance.
Oh wait,
no, it's in flight again. Hey, we did it.
Oh, it worked.
Okay, we did it. Look how good we are.
But what did I change? Oh, I know what I changed. The less than to less than equal. Hold on. Whoops.
That surprises me, but I'll go with it.
Okay, hold on. I'm also, oh my God, I have 1,000 steps. I forgot that I was demonstrating it. Okay.
There you go. It bounced. Perfect.
Okay, yes. Perfect. I don't know. Okay, it's working. Great. Okay, so, and let me just take that comment out. Okay, wonderful.
Put the
now let me
back
just see.
On as well.
I'm just gonna crazily put this back in. Yeah. So what it is that if when it hits the bottom, if it goes below the bottom, and then it's leaving, but it still hasn't made it above, I'm sort of pinning it back to the bottom. So if I'm checking greater than or equal, it can sort of think it needs to go back into stance, even though it's moving upwards. I could do something with the velocity, but anyway, regardless, we're gonna be happy with this. Okay, so
let's
now
throw
we
the
put
damper back on, because I don't think will help. That'll help for the next phase, I think.
Let me do this. Yeah. Perfect.
Then we need amazing. Now we need to detect This is perfect. Look at that. That's exactly right.
Okay. So now I'm going to, I'm gonna ask you to help me with what is next now for getting it to. So just to pause for a second, our goal is, let me do this. We have some like desired apex, right? And that's going to be the distance from the bottom to some value. So let's just call that 200. And what I'm going to do, just so we see it as a reference point, is I'm going to draw a line from 0 to height minus, and again, we have this weird height minus thing, but I'm just going to draw a line so we can see it. And so the goal is to get it to jump to that desired apex. And actually, I want to take out this mouse press thing. That is irrelevant now, because the rest length is just 100 right now. So it's going to settle at 100 pixels, and we want it to get to jump to, it's going to settle at 100. We want to get it to jump to 200. Okay.
We tell it to jump. It asks how high.
Yes, exactly. All right. So now what do I need for my phases and et cetera?
So what we're going to need to do is detect what is the apex. So we need some way of detecting the apex for each jump. So this is going to be what the kids call a state machine, if you will.
Yes.
It needs to keep track as to, like, are we in the air, which you already keep track of, or are we on the ground? So when we enter the air after having been on the ground, we should reinitialize a variable, which is the apex height, which we keep updating throughout the flight phase if it's greater than the previous apex height. And so by the time it hits the ground, we'll have stored the maximum value of height.
So I'm going to have a variable called like current apex, and that's just going to be initial. I could just initialize that to 0, I guess, or I should give it the rest length. Yeah.
That seems fair.
Okay, I'll put it at 0. By the way, the other thing I'm doing is, even though we have this sort of some state checking here, this state checking is really about updating the anchor and the forces. So I'm gonna, just for the sake of working on this Raibert algorithm, if that's the right way to phrase it, I'm gonna have a separate function called update phases where we're gonna do only that, which I think will help. We'll see. I might be over organizing this, but okay. So what I need to do is, like, first of all, if the phase state, I should just call it phase or state because it's hard to type, is in flight.
Why not both?
This is now what you're saying is I want to check to see if its current apex, I want to calculate if the is greater than its current apex so that I can reset its current apex.
Correct,
so I'll say
correct.
So I'm going to just say apex equals the height minus this dot Bob's y position. If apex is greater than current apex, then apex equals current apex. Oh, sorry, current apex equals that apex calculation.
Yep.
Does that seem right to you?
And the only tricky thing we're gonna have to do is when we're in stance, we're gonna have to like reset that, like, but without erasing it, because we need to use it for the actual push off, right? That's gonna be the other tricky part.
Is this really current apex, or is it like it's like apex record or like best apex? Highest
current apex is
fine. Okay,
it's fine. It's just I think on some level we do need some way of detecting if we've changed a state, because yes, that's going to tell us whether or not we have to reset.
So we can see it here because I have a line which is showing, and I'll just give this a color.
Perfect. Yeah.
So I'm sort of picking some arbitrary colors here. The red line is the desired apex, and the blue line is the current. But I need to do we need to have like a previous phase? Do we have to store a previous phase to know if we switched? Do you think? Because if we store it's up to you. We do, but let's. I think it's okay.
You did it.
Yeah.
I think you did it.
Because it's kind of we might have to clean this up a little later, but yeah, we can see this is working. You're right that there might be some wonkiness, but but I think we're going to be adding other things in terms of that we can figure out if we need to when we need to reset it.
Great,
because
it's
good. In flight, it's going to
as long as we have it stored for the stand. As long as we have it stored while it's on the ground or in the stance phase,
and I can actually this might actually be better, right? This looks right because if it's in stance, the apex is just the rest length. Yeah.
Great.
Okay. Great. Okay. What's next?
Okay. So now we have that stored. So now we have to detect when we're at the bottom.
Right.
So because once we are at the bottom, and I think the easiest way to do that is we store the previous height when we're in stance and the current height. And if the current height is greater than the previous height, then we're starting to ascend, which means we were just at the bottom and we should push off and therefore add a little bit of rest length to the spring.
So are we already detecting that here, basically? Oh, no. Here?
That's when you're in stance, right?
No, but this is when we switch to flight.
That's when you switch to flight. That's when you're past the rest length of the spring.
That's
when you're about to take off the ground, but not when you're at the bottom of the motion.
Bottom of flight. Okay.
Yeah.
So we're gonna
that's what will allow us to really inject some energy into the cycle.
So what's the difference between current height and current apex? Or is it the anchor position that we're talking about?
Sorry, repeat that?
I was realizing, what I was about to do to detect this is, you said current height.
Yes.
But what's the difference between current height and current apex? Was my.
Well, the current apex is being updated during the flight phase.
Right. Okay.
Right. I mean, I'm just trying to. I'm doing a little bit of code engineering in my head at the same time as the math here. But what you need to do ultimately, you have to keep a track of what was the last apex height, and you can store a previous one as well. The last apex height, and when are you at the bottom? That's the things you got to know.
Got it. Okay. So I'm going to make a variable that's previous apex, and I guess, so previous apex is right after I calculate the apex, I can save it as previous apex. And then I'm looking at, okay, I'm a little, I'm thinking about this here. So I'm comparing the current apex, which is just, again, it's, I can call that H. I'm going to just do this at the top here, even though, so I think what I'm going to do is have H be this. This is the same thing. I'm just going to be using this value a lot. And then, and I wonder if that should, I'm going to make that a global variable just for right now. Because what I want to do is only people in the chat are giving me, I'm struggling here for a second. So we're updating the phases. I'm getting the current height of where it currently is. The previous, I think I should call this a previous height because it's different. The apex is really tracking like where the record kind of is.
Correct. And it's a condition on that as whether or not you actually were, was at the apex as opposed to what the current height is, which is.
Yeah. So H is the current height. I might be sort of losing my mind here a little bit with these different variable names.
It's okay. We're close. I think we're close, dude.
Current height is where it is.
Yep.
The previous height is whatever the current height was right before I get the new height. Okay.
Correct. Yes.
So now how are we comparing these for this next phase detection?
So next phase detection, you say if the current height is greater than the previous height, and I'm assuming we're in the stance phase for this condition, right? Then we've hit the bottom, right? So which means we should enter a phase where we're at the bottom, and which means we add some whatever our change in rest length is.
Got it.
And it'd be helpful to do it as a go ahead. Yeah.
If the current height is greater than the previous height, and we're in the stance phase, correct?
Yes.
Okay. That means we have hit the bottom, and we have a new state.
Phase.
We have a new state, yes?
Yep.
Which is?
Yes, new state. It's helpful to be in a new state here.
And what do we call that one?
We could call it the push-off phase if you want.
Push-off. Okay, that'll be state 2. Phase state equals push-off. And we should be doing these, I think, with else ifs. Okay, so I'm not, like, one thing we should do is just, one thing that we should do is just make sure we get to this state. Okay. And Alka is asking, did I remove the declaration for current height? I did. Thank you. So I have desired apex, current apex, previous height, current height. The previous height is what the previous current height is this. And now I might have done something where I'm using H, whereas that's really the current height for the apex detection. Okay, let's see what happens. Previous apex equals apex. So that is actually current. Okay. Previous apex is, I lost my calculation for the apex. I guess that's the current. What happened? Let's go back to flight for a second. Okay, so if we're in flight, we're looking at what there's current apex. Whoa, I renamed some things. Current apex is just the current height. I might be having duplicate variables here, but that's okay.
If you're in the flight phase, right? Yeah.
Yeah, if you're in the flight phase.
It also, there's that condition on it. It needs to be higher than the previous height, right?
Yeah. Previous apex.
Why are we adding? Because you already have this current apex. You're updating it. You're updating it in that if statement right there, right?
Yes. I don't need previous. If current height is greater than current apex, current apex equals current height. I lost something that I had working here. Okay, wait. Okay, hold on. Oh, we got to the push-off, which is fine because we got to the push-off phase. And let me just comment this out for a second to make sure everything else is still working. Yeah, everything else is still working, but this is good. We see the push-off phase detected. We did nothing in it, so it just squashed itself. So what do we need to do? So I think we're good, even though I've lost track of a few things. So what do we do in the push-off phase?
Everything is the same in the push-off phase as in the stance phase before, except once we've entered the push-off phase, so like the calculation for whatever our force is, our spring force, adds a little bit more to our rest length. I forget where you do that in your code, but
yeah, well, I haven't done that yet. So one thing we could do is just, and I think it would be useful, like I remember in one of the MATLAB examples you sent me, there was like, it's good to know the original rest length, which could be called the nominal rest. So basically, the spring is getting that nominal rest length when it starts. And what we're going to do to push off is we're going to say spring rest length equals nominal length and plus 10. Like I'm just going to, or let's just give it a hard-coded value. This is what we're going to control with the controller, right? So if I do this, okay. Oh, nominal length must be spelled wrong. Nominal rest, I called it. That's fine. Where was that code? Update phases. Here we go. Okay. Let's give it something much bigger. Oh, you know what? We need to apply the force. Yep. There we go. Okay. Okay, so one thing, so this sort of worked, but you can see that it hopped, but the thing is once it leaves, it needs to go back to that nominal rest length, right?
Correct. So like once it's in the air, you pull back the leg, yeah.
Right, so in the flight, and this is really kind of, I could do this in so many different places, but I'm just gonna do it here. I'm gonna say the spring rest length needs to go back to the nominal rest. So there we go. Okay, hopping robot. I mean, it's hopping, but I've just hard coded, and just to like see, like if I make this 10, it's a smaller hop.
Yep.
And if I make it like something way too big, we're gonna see it just like fly away. Great. Okay.
Yep. There's gone.
So now we need the controller goes here, right?
Exactly. So now we just need to change how much that is changed. That 300, we now connect that to the error.
Hold on, breaking news. I did something like I wrote some JavaScript code that like I should make sense in my head, but doesn't. I can't say, like this makes sense pseudocode wide. If the phase state equals the stance or the push off, but no. I have to say this I have to check if it's either of these.
Yes.
That is the correct syntax.
Well, let's see if it still works.
Let's make sure we didn't get lucky that it worked with that mistake in it. So where do I do that? Yes. Let's do it something reasonable, like 20. Okay. Yeah. That's, let's make it something much less. Great. Okay, we're good still. Okay, right. Back to, so this is the delta length that in your lecture that you showed us the formula for. So now we just need to calculate that based on the first thing is the error, right? Current apex minus desired apex minus current apex, right?
Correct.
Okay. And I'm desired apex minus current apex. Okay.
And we need to have a little gain, some kind of KP gain to multiply it by that we have to choose.
Let's make that a variable, and I don't know, I just picked a number from a hat.
So that's fine hat. It's a fine hat.
Actually, you know what? Even though it makes sense for this to be a global variable, we're going to be working on this entirely here. So let's just put it here. Okay.
I'm not upset. All right.
Okay.
This is great.
What's
we'll do
next?
some vibe. So we'll be tuning the gains. So much of controls is tuning the gains, and this is what we call vibes-based tuning.
Yes. And then what's next for the delta?
So right now, so your delta, you can just create let some variable call your delta length, and then said it's equal to kp times your error.
Okay. We're doing just the p right now. Is that right?
Let's start with the p. Let's keep it simple. See what happens. And we'll mess around with the gain, see what happens. Because if it's 0, it should do nothing. If it does a little bit.
And now, the thing about this that I'm just checking, if it's lower, it's going to be, I'm just thinking about the y position thing. Oh no, but I've already done that in the way that I'm calculating this. So let's just see what happens. Yeah, it's going, I think I might have a directional error.
It's possible.
Or no, or maybe we just need
try a higher gain here.
Yeah. Well, it's definitely trying to get to that apex.
It's definitely getting somewhere. Let's see here. Yeah. The
oh yeah.
So yeah. Also, I think DJ points out in the chat.
Yeah. That is correct.
That the apex is not. Yeah. That's
some reason. So
we lost the ability to. Yeah.
Yeah. Okay, so let's fix that.
We got to make sure we're tracking the apex.
Yeah, current apex does not equal the current height. Okay.
Yeah, so I think that so we want to make sure we didn't accidentally overwrite because we had code that tracked it to be the apex. I don't know if we added some extra code that changed that.
I think I did. So first of all, the current yeah, okay. So let's think this through. When we're in flight, what we're looking for is whenever the current apex is basically, so I'm just going to rename this variable for a second because it's confusing me. I'm going to call it record apex. So this is like the highest apex that it's been. If the current height is greater than the record apex, then the record apex should equal the current height. However, I just had this extra thing in there. I was like, now that I renamed the variable, which was now unnecessary because it made me notice and so I think the only other place this changes then is this. So let's just see if that's okay. And then there's the renaming a variable had unintended consequences here, but let's see if this is right. Yeah. So now, however, I need to reset the record apex. I renamed it everywhere.
Correct.
Okay. Yeah, so it should, okay. Now the question is.
Yeah, put the KP down to 0 if you could for the moment, just to make sure it still works here.
Yeah. Yeah.
Okay, good. That looks like it's working. Okay.
Okay. So let's look at the let's look at the error just to understand the direction of the error.
Yeah, so a little small. The console's a little small at the bottom of the screen here.
Yeah. All I'm seeing is 100 because once it's in stance, it lost the. So I lost the record apex. So I think I might be confused about the order that these phases are happening.
Okay.
Like, should it go from flight to stance?
To stance.
Yeah.
And then to push off. And then back to flight.
Yeah. So where am I? I think I need to not be setting the phases here. Because that, I think that's causing some conflict in the order. So I'm just gonna, I want this, we're gonna make some updates here because I want this section here to only be physically applying the forces and moving the spring. I want all of the phases to be managed in this function. So right now, Say again the order of the phases. It's starting in flight, right?
Correct. It's starting in flight. I'm gonna try to make a little diagram that you don't have to make me big. You don't have to make me big. I'm good. Okay. I'll make it so you can see me.
Okay.
So flight. Then you're gonna go to stance. Then you're gonna go to push off.
Got it. So I think setting the record apex in stance is a problem. Resetting it back to the rest length, because the whole point is we need that for when we do this push off calculation.
100%. So basically what this means is that, what's helpful is that if you do a reset during one of these triggers, when you do it on the trigger, you don't have to worry about it. So that's why, so if you keep track of what the previous thing was, then you know when the trigger happened.
Right. But also I think that I can just order this in a way where the check for moving from flight to stance is here. So for example, this was our check for moving from flight to stance. And then now I'm going to check to move from stance to flight and I have some variables for this, like I have current height is greater and the velocity. Okay. And then
Aristachos talks about putting it, we can just do when we detect the bottom, like when you actually add that thing, that's perfect time because we've just used it and you're done.
Yeah. So now I'm going to this is not going to flight. This is going to push off.
Oh.
Right? This is it hitting, right? Because no. Hit the bottom. Sorry. I have it in the wrong place.
Yeah, it's fine. That's supposed to be flight. That's supposed to be flight there.
There's a stage after push off. We have flight, stance,
you're back
push
into
off.
flight.
Oh, just back into flight. Okay. So I can do this. I'm going back into flight, and here is where the rest length would then go back to, the current apex. I've done that because that's happening in flight, even though these things could move around. Yeah. But this is where the record apex starts again at the rest length.
Cool. Awesome.
Okay, so let's just review this to sort of think about it. So we're saving the previous height. We're calculating the current height. If we're in flight, the rest length is the nominal length as it's flying. We're checking to see if the record apex is updating. And if the anchor hits the bottom, we go to stance. Once we're in stance, it's going to be compressing a little bit. So once it's moving, doing that, this current height is greater than the previous height. Oh, it's compressing. We're detecting the moment it stopped compressing and it's turned around. That's its push off. We apply a rest length that is already doing that, which is going to change the spring rest length. Now, do we get a force calculation of the spring forces there? Yeah, it comes around. It should do that. The order should matter. Okay, let's try running it. I think this is right.
Okay.
Just for the, and let's just go back. The KP is at 0 right now. So, okay. So that's with the KP at 0. Now, let's give it a KP. Okay.
Let's do 0.01.
0.01. I just wanted to okay. I'm gonna have to restart. Okay. Yeah. Okay. I think I think the gravity might be kind of strong right now, in terms of like keeping it from that spring force being able to do much. We can also just try tuning it up a little bit. Yeah. There we go. It's
not bad.
And let's give it a less of a desired apex just to see that we know it can overshoot that. So yeah, there we go. So am I assuming that maybe like what we need now is the other parts of the controller?
I think so. Yeah, I think that this is great. It looks like it's working. Like if for instance, if we just made KP like 0.10, like we should probably overshoot a bit. Would be my guess.
Yeah.
Yeah. Good. Oh yeah, it's perfect. So yeah, so if we get out the other parts of the controller, the KD and the KI, I think we're in good shape.
Okay, let's do it. So I don't remember what I'm doing for those.
so this is great. So what's maybe the KD can be a little easier to implement, and so. We tried doing that. So like technically what we need is the derivative, and if that's going to be the change over time in our error, right? So because
this previous error.
This is happening. Yeah.
Oh, my internet.
Derivative. We're doing a discrete derivative, which is literally subtracting one from the other, from the one step to the next.
So I need the previous error. And so to do that, I also need this error to be a global variable. Again, there's other ways I could sort of manage this code, but this will make things easier. So now right before I calculate the error, I'll save the previous error. And then this should go at the end. Whoa. Did I lose the delta length calculation? Wait, hold on. Let me undo a few things.
Okay, it's fine. I'll let you drive.
Oh, yeah. Oh, right. No, we're good. Delta length, okay, I see. The delta length is KP times error. Now we're going to do the derivative. I hadn't done it wrong. I just got confused. So previous error equals error. Make both of those global variables. Now we're going to I'm going to have like delta error equals, is it error minus previous or previous minus error?
The change would be error minus previous because that's what I change over time.
Okay,
so yeah,
great. So I've got that, and then. And is that just another component? So KD
times just added that component right there.
Delta error. Okay. So let's do this. It's kind of getting a little closer each time. Do I maybe want to tune these values?
Let's do a little vibes-based tuning here. Let's see what we do. Let's try a little bit of. Actually, I would lower the KD a little bit. See, it's getting a little closer. It could be too high of a KP. Maybe bop down the KP by about half. Okay. Maybe a little more KP and keep the KD the same.
I should make these sliders.
We might also hit the point where we want the integral gain, because when you have like these errors that accumulate over time, we might want the integral gain.
Yeah. Also, these values really make a big difference.
That's actually not too bad. Look at that.
Yeah. Like if I give a little bit more, I might have ruined it now because I gave it more spring force and less damping. But yeah. Okay. Yeah, that's not too bad.
Not too bad.
Not too bad.
Now let's try a different apex height to see if it works for another apex height real quick, just to see where we're at. Yep, going higher. A little bit of overshoot here. But yeah, it's definitely responding to the new height change.
Yeah.
So maybe... So this might be a... I wonder if this is a derivative... Oh, look at that. And there sometimes can be limits on how well it can work for like vast changes in height. But the idea is that like it's good enough, like in the context of legged locomotion, it's not often as important to get the exact height that you want, but if you get it in the right area, that's enough to keep it running and it regulates. And if it's hitting the ground, I'm not sure if it's hitting the ground at a certain point, like the terrain is rough, it's just kind of got to keep going. So and this is like good enough to keep it in the air and moving.
Yeah. Yeah. Oh, this is amazing. I'm very excited by this.
Well done. Good job.
Okay, should we add the integral just to finish it off?
Yeah. Sure, we could throw in the integral term. So we just need a running error accumulation is what we need for that. We're just going to accumulate the error with just a running sum.
Okay. So I will make a variable called like error sum.
Yep.
And Sounds then good. I'm going to are we accumulating the delta or the raw error?
The raw error we're accumulating.
Okay. That's what
Yep.
I was just testing you there to make sure. Okay.
Of course, absolutely.
So error sum, and then I have a ki.
Yes, and a ki.
And I'll just leave that as this. And so now I'm just adding.
Yep, just add that term to the controller.
Okay, so hold on. Let's make this look a little nicer. So this is
Sounds good.
Proportional control. What do I call these little? I'm going to say proportional, derivative,
integral,
and then integral. And what I'm going to do is I'm going to put the previous error up here. So basically, the error is the and I guess, this is fine. The proportional control needs the error. The derivative needs the delta error. The integral needs the error sum. So now I'm going to say plus ki times error sum. Okay.
Yep.
Okay. Let's see what happens. Oh.
So ki you want to make real small, maybe. Small. I think it would be the lesson here.
Yeah.
And this is actually kind of a lesson that sometimes so one thing we know is that the thing that's most likely to make your controller unstable is the integral term in things like that. So it's possible you don't need it. Need it. So maybe it's just, or I mean, it could be there's some kind of sign error somewhere, but I think it might be it's just not helping you right here. But weirdly enough, like I'm looking at that error, like that error is positive.
Yeah.
And
so I just said minus ki, and it's like tuning it quite well. Oh, now it's going under.
Now it's kind of drifting down. It might just be let's try that here. It could be a magnitude thing.
Yeah, we might have a directional issue, but
yeah, it's possible.
But because it is but it is drifting too high. With minus, it's drifting too low. I wonder. It's just
a silly thing really might be like literally like throw. Yeah, make sure obviously 0. We'll see how it behaves at 0. Like, so what should be happening is that the error should be slightly negative at each of these jumps, right? Because you're going past where you want to go.
Right.
So it should be accumulating a little bit less of a delta error change, and it's not quite doing it. Like it might be as silly as serious because the units involved here, it might need to be a really small number.
Yeah, JavaScript, precision is. Now, do we see that this is pushing it slightly higher each time, or maybe that was not enough? So one thing is like we're at 120 now, just looking at the time. So there is sort of like a secret thing I can do here, which is we've kind of gone through coding this. Oh, you have to no, you don't reset the accumulative error. Sergio is saying, I think you have to reset the accumulative error, but the whole point of it is.
Are you resetting the code every time you reset it? Because then you should reset it. You don't have to reset it in the loop.
Yeah.
But you want to reset it when you reset the simulation, though.
Yeah, it's starting at 0 each time. Yeah, this was counterintuitive to me. So when I first looked at Christian's MATLAB code and was like porting it, I was like, this is insane. There's a value in this like physics simulation that doesn't like get reset at each moment in time. And then I realized like, oh, it's the integral. So here's the thing. I think we should. This is I think this is pretty good. Like we've gotten this like 90% of the way there in terms of the logic and these values. I think what we should do are a few things. One is I actually have a version of this that I made a few days ago that works a little bit better after I looked at your MATLAB code and got the explanation. So I think I could pull that up and we could kind of look through the code and see maybe where see if we see anything there in terms of how it's implemented that might be the key to what we missed here. The other thing is I think we could have a brief discussion around how you would take this to 2D. And I will show a hopping robot that has no controller, but has all the 2D spring mechanics, and kind of leave that as a prompt to the audience. What I'm going to do is make a page on the Coding Train website for this stream, and it has that passenger showcase feature. So if you create your own version of the hopping robot from this stream and improve on this, you can submit it there, and we'll have a gallery. And at some point, I'll come back and look at some of them, or we'll talk about them in the Discord or somewhere on social media. And then I can sort of say, I got so like locked into like worrying about whether we were going to get this to work that I lost track of the chat. So we can also take a few questions. So let me start with this. I'm going to save this as is. This code as is going to be released. Obviously, it won't happen instantly because I got some stuff to do today. But within 24 hours, this code and all the metadata for this stream will all be in the video's description. And if anybody wants to help with putting that together, you can, tag me in the Discord. I always welcome that because I'll time code it and all of that. Let me go to the P5 web editor. I'm going to go to open because we have to come back and do more of this because what I'm going to do is I'm going to look at this working Raibert. This was so you can see here. This has very similar stuff. We've got a KP, KI, and KD. We've got a phase flag. We've got the current apex, current bottom, prior apex error integral. So we can see, and let me just run this one. This is basically exactly what we were attempting to build today, but it works quite a bit more accurately. So, but you can see it's exactly the same code. It has a bob, a spring. It's the same code base. I built it in the same way. I just did it slowly with not live. And you can see here, we've got this update phase function. So let's just look through this. It's got a switch statement. Oh my goodness. Some longtime viewers of the Coding Train will be shocked the fact that I put a switch statement in here, but I thought
this was my fault. This is my fault, I believe.
Right. It came from MATLAB. So this was me implementing Christian's MATLAB code, which will also, if it's okay with you, we can share as part of this for reference.
Yeah, sure.
Okay. So you can see case one is flight. But flight was divided into two, which maybe might have some advantage that I might have missed here. I'm not sure, but we can see that we're tracking the height relative to the current apex. And if the velocity starts pointing down, we switch to, and I forgot to put my computer on.
It's like a falling phase. I didn't name it. Yeah.
Yeah. So the phase flag goes to 2. I have to do something here because I'm getting some spam and I forgot to put my phone on Do Not Disturb. It's now on Do Not Disturb. Okay. So then we go to flight post apex when the bob's Y. This is exactly what we're doing. Oh, that takes us, and then we're tracking when do we hit the ground. So this is we're tracking when we hit the ground and it goes to stance, all the same. The difference is here then we're tracking, this is now tracking, is it compressing? It's compressing. What point does it turn around from compressing? And then we do this proportional, the controller. And so let's look at this. We have the error, desired minus current. I don't know if you could hear that. My stomach just grumbled. It was like a comical grumbling sound.
Your stomach grumble is filters are very good on your streaming software.
It's too bad because it was like it was like a sound effect from like an old style variety show or something. Anyway, I need a stomach mic, separate contact mic on my stomach. Okay, derivative apex error. Now look at this. Proportional apex error minus prior apex error. -1. I don't know. I have to think about this more, but I do have a -1 there, which might be a key to
it's
something.
It's possible I put the -1 in there. I forget. I was pretty tired when I was coding this. So
it's honestly the P5 pointing down. It's where we start to sort of like lose confidence in our brain's understanding to know which way is up. Okay, prior apex error, apex integral, spring rest length is nominal length plus these. So you can see it's the same exact code. Interestingly enough, the only thing I'm noticing, and then we go to case 4, which is it going 4 is just, it's just resetting some stuff and setting it back to 1. Okay, this is like resetting the rest length, the apex height, and the current bottom height. So case 4 isn't really a state. It's like an interim. It's like what you were talking about, detect the change, do this one-time thing and go. So just out of curiosity, I hate to be so this is definitely my style. If I go here and put a -1 here, what does that do? This was mine. Nothing has really changed, but if I give it a little bit more integral error,
it's staying on one side.
Yeah. So
it might not be doing very much.
This is a good audience interaction. Somebody will take a look at this. I certainly won't be able to sleep as well until I take a look at it later to see what the differences are. So anyway, I'm going to release both this reference of the working one so people have it if they want to start to expand on it, as well as the sort of messier one that we did live. And then the other thing I might mention that might be interesting as like an exercise if people are thinking is to what extent could this update phase be part of either the spring class or the Bob class, might be to think about something as that you could do. And then here's the next step, which maybe we would, after we kind of think about this, clean this up, what would be really fun to come back and do, and I'll show you this, is remember this is what we started with today. And I was trying to see if I could catch any questions, but this is what we started with today. And we started to build the controller into this. So what I will also release with this stream for anybody who feels so inclined, but I would like to, maybe in a month or sometime, at least this fall, let's not wait 3 years. I think it would be nice to come back and look at this 2D hopper. So what this is this has no controller built into it. It's exactly what we did before. Let me just show you. I'm going to make the angle 0. Right? I didn't draw the squiggly spring, but this is exactly just the hopping spring. However, what you'll notice is there is a bit more trigonometry involved in how I'm detecting the foot position, the bob position relative to the ground. Right? I'm using the right triangle that's made, and if we weren't already at 130, we could draw a diagram and go through this a little bit more. But you can see that I'm basically, and this is just there's no stance or flight in this example. There's just a Boolean variable stance. So you're either, if you're not in the stance and the bob position is has left the ground, you go. If you're flying and the bob position has hit the ground, you go into stance. And if you're flying, you need to update the foot position relative to the angle while you're flying. If you're in the stance and you've compressed below the rest length, then you start to fly, which again could use a little bit of, but you'll notice the spring force, the damping force, those are the same because those were all vector maths before. So just the stance and flight detection changes once you have an angle inside, the robot is at an angle. And so you could say, I could do something quite extreme where I could say it's in radians. I could say, 45 degrees, and it's just going to fall right over, or negative 45 degrees, right? So
in fact, one thing that's cool that you can do is quick thing you can play with is you can turn off damping, try to give it an initial horizontal velocity, and try to see if you can pick a horizontal velocity that it keeps hopping for a few bounces with a certain leg angle.
So the horizontal velocity, I can give it an initial horizontal velocity. And then...
So for that, it's tripping forward. So you're going to want to make the leg angle a little more extreme. And
I would think if I make it more extreme, it's going to, I see. Oh, I have the radians.
You're turning those are yeah.
Yeah, I forgot that I had it in degrees. It's just going to fall right over.
Let's do 0.1. Try 0.1 here. Sorry, I'll guess the opposite. You want a positive 0.1. I'm sorry.
Yep. Oh, that's gonna. But it immediately started going backwards.
So yeah, maybe 0.01.
So like, but we get the idea.
Velocity.
And I could also give it. like a much bigger velocity to start with.
Yeah.
And
that kind of thing. But yeah, exactly.
Yeah. So you get the idea. So this is fun. So this is, I think, it would be interesting to come back. The other thing that I think we could consider doing again is sort of redoing this with more of a sophisticated physics engine that's going to handle a bit more. But I think the interesting thing is once you give it over to a physics engine, you know, detecting the phases is a little bit less in your purview because it's kind of like managing, like, when is it actually leaving the ground? So anyway, regardless, these are, so let's review here. I have, what I'm going to release with this stream is, and let me rename this. I'm going to rename this to 1D Hopper Live. Okay. So this is what's going to get released with this stream here. This is what we built today, 1D Hopper Live. This is a working Raibert controller that we made a few days ago just to be sure that this concept would translate from MATLAB to P5JS. And then I have the starter code that I used to make this today, and then starter code for a 2D hopper that you could try on your own. And so
and if you want to release you can release my MATLAB code that I gave you. That's all fine as well.
Yeah.
If anyone has MATLAB they want to run it in.
So I'm gonna just show you. We're gonna kind of like, if you had a quick question you wanted to ask, I can take a couple of those. I missed them. If you asked them like more than a minute ago, I could scroll around and look. But what I'm going to, what just happened here? What happened to the coding train? Oh no, it's just my internet is being bad. People were asking about why is it a stick instead of a spring? So both were springs. I'm just drawing a zigzag to make it visually appear more spring-like. By the way, you could do this with more than one leg, right? Even in 2D.
Yes.
That could be really interesting as well. So for some reason, my internet is just not complying, which is very frustrating. Nature of Code site worked. Coding Train website here we go. So I just want to let people know where this is going to show up. There is, on the website, there's this track called Coding Train Live. If we go here, these are, and I really should I never made one, like this is just done arbitrarily for a few different live streams. But like, for example, if I go to this live stream, which I did on sentence embeddings, you can see the code examples are here. There's a description, references of links that I looked at. So basically what I'm going to do, and it might take a little time, is make a page for this live stream. This link will be in the video description, and then you'll be able to find all of the resources, as well as then you'll be able to see here, if you go here, submit to the showcase, what you'll be able to do is there's a form here, and you'll be able to basically like enter in your sketch, and it can show up and be featured on that page for additional Raibert controllers. Whether you make one in P5JS, you make one in Python, I don't know, do a 3D one in like Unity or something. It would be exciting to collect a few of those from the audience. All right, I'm gonna put on a little music here as we say goodbye. Christian, is there anything else you wanted to say?
Well, first off, thanks for having me again. This was great. I'm glad. I look forward to continuing this for a future time. But we got it working. We got a little 1D hopper going. Yeah, that's really, and getting the phases together. We got the infrastructure together, and I think that from this point on, like, I think what you showed in that other piece of code is pretty close to being able to control the speed. That's where it starts to look really cool. And you could even try to get the balance in place if we wanted to with that. Right. So pretty cool stuff. So thanks, Dan.
Yeah. Oh, and I meant to ask you this. So now you obviously you teach, You've got your lab. I know by following you online, you've made different appearances on some other channels, YouTube channels, podcasts. Where should people, if they want to see, like, you've got this great setup. I see you've got an amazing whiteboard behind you. If you're doing more lectures and more videos just about robotics on your own, where should people find those and find you online?
Well, I mean, you can follow me on most of the social media platforms at Hubicki, Chubicki. So Hubicki. Hubicki, I believe, is canonically Chewbacca's younger brother. I'm not sure that's canon though. But so Blue Sky is where I'll post a lot of my like if I'm doing something, I'll post it on Blue Sky. I do have a YouTube channel, which right now has a couple public videos, but that should change, I think, pretty shortly. I'm on leave this term. So I'm gonna try to really try to pump out some more content. But yeah, so you can find me on Blue Sky, on Insta, on X, and Christian Hubicki on YouTube.
Great. So I'll make sure to tag and put a link to Christian's YouTube channel, at least in the video description, as well as the other stuff. So that's great. We did it. We only went about 40 minutes over. I will say the last time we did this, we went 3 hours, and like, yes. I stopped myself because I very easily been like, oh, let's just go a little longer. We'll get the 2D thing working because we have all these pieces. No. We're going to be civilized. We're going to allow, we did this. It was a nice long stream. I hope you I learned a ton. Again, I drew so many connections between stuff that I'm already doing in the Nature of Code materials. I hope we can come back and do a part 3 where it probably makes sense to just do the 2D hopper, but maybe there's some other ideas that you have. And so, I meant to say, and I didn't, so if you're wondering what is next for the coding train, I had mentioned that I'm planning to do weekly live streams on Mondays. That is still the case. The last time I said the first one would be September 8th, but a conflict came up with me with my NYU schedule. So I'm going to be kicking those off September 15th. So who knows? It's not impossible that there wouldn't be another surprise stream between now and September 15th. I've said that each time. I don't have any topic planned, but look for me, look for those events to get scheduled on the channel. Going to, the best place for you to follow when I'm doing the streams are the Coding Train's, you're not seeing my screen here. The Coding Train's Discord. So you go to thecodingtrain.com/Discord. It'll take you to this page where you can join the server. That's where I will post announcements and updates about my schedule. All right, thanks everybody. This was super fun. Great. I really hope that you make, some people make some of their own robot controllers and improve on our code and share those back. And thank you again, Christian, for being here. This was really fun. And I'll see you all next time. Now I'm gonna play the song out of practice. Oh, I don't actually have a screen to go to. This is my thing. Like my setup was, so my previous setup, this is my new setup. So now I'm just gonna have to talk for like a minute. But I'm gonna hit the finish button in a second. I had an outro screen. So I would say goodbye and I'd flip to the outro screen, put on a short bit of music and then hit stop. Now I have no outro screen. So your outro screen is me. I'm gonna let Christian off the hook and just move back to here. Your outro screen is just me talking a little bit. So thanks very much. I hope you're all enjoying your summer. I know a lot of people are getting back to school. You got a little time left. Enjoy that time. Get outside. Be with the people. Be with the humans. Hug your friends and family and neighbors. And I don't think we need to listen to the end of the song. I'm gonna hit this finish button, say goodbye, and see you next time on the Coding Train. All right, here we go. Goodbye.